Welcome to this second part of the chapter Data Structure. In the previous part, we have discussed the introduction to data structure, and in this session, we will be discussing stack and queue in detail. As we are starting with this second part, I assume that you are well familiar with the introduction to data structures and you know the definition of data structure, the difference it has with data type, and you also know the different types of data structures that are there and the two data structures that are in your syllabus, that is stack and queue. Okay, so let's start this video lesson. Now the first data structure that we have is stack. A stack is a linear structure implemented in LIFO, that is called LIFO, last in first out manner. LIFO means the element last inserted would be the first one to be deleted, like a stack of plates that you see in a marriage ceremony. So what happens? The plate that was put there at the end or at the last will be removed first. So that's why this data structure is called LIFO implementation. Last in, first out. The element that was inserted last will be removed first. Okay. In stack, insertions and deletions are allowed at only one end, and that one end is called top. Okay. So this data structure shrinks and grows from one end only. The other end is fixed. Okay. And that end from where the insertion or deletion takes place, that is called top. The insertion of element in a stack is called push operation. The name given to it, the technical name is push. And the removal of element from the stack is called pop. So there are two operations, push for insertion and pop, that is for deletion. There are some other terms that are related with stack. Those are peak, overflow and underflow. Peak refers to inspecting the value at the top of the stack without removing it. Please note, it refers to checking the value at the top of the stack without removing it. Just have a look at the value that is at the top. This is called peak. What is overflow? Overflow refers to the situation when someone tries to put an item in the stack that is already full. Okay, so when you try to put an element in a stack that is already full, that situation is called overflow. This situation occurs when the size of the stack is fixed and cannot grow further. Okay, or there is no memory left to accommodate the new item. Next term is underflow. So underflow refers to a situation when someone tries to delete or pop an item from an already empty stack. That means there are no elements in the stack and you are trying to pop an element. So that situation is called underflow. Okay. Stack is having no item in it and still one is trying to pop an item. So this situation is called underflow. In Python, the stack is a dynamic data structure as it can grow with increase in the number of elements or it can also shrink with decrease in the number of elements. Okay. If it is implemented in static manner, then it will be having a fixed size. Okay. If you implement stack in C or C++ using arrays, then it has a static implementation. There you will have a fixed number of elements allocated to a stack. But in Python, it is dynamic. It will grow and shrink according to the requirement. Okay. Now, how it is implemented in Python? In Python, we use lists to implement stack. So Python offers a convenient set of methods to operate lists as stack. So before working with stack and queue, you must be clear with all the methods and functions of lists. Okay. So if you are not aware with the methods and operations, you can get back to the class 11th chapter on lists and you can make yourself aware about all those methods, and then you will find it very easy to implement stack in Python. So if you are implementing peek operation, then you can use just stack and in the square brackets give the value of top, and if you print it, you will get the value that is at the top. You are not removing it. Okay. You are just printing or accessing the value present at the top of the stack. So this is called peek operation. Here the stack is a list. You will create a list. The name of the list will be replaced by this at this position, and the top will be the integer value. And what will be its value? It will be equal to the length of the stack minus 1. Why minus 1? Because the implementation of a list starts from the index number 0. The first element is placed at the index number 0. That's why this minus 1 is there. So the value of top is length of the stack or the list that you have created minus 1. And if you are implementing push operation, then what will you write? You will write the name of the stack, that will be the list, dot append function. You know append function? It adds the item at the end of the list. Then you will provide it with the value of that element. So it will add the element. So it is single line implementation in Python for peek, push and pop. Okay. So for pop, what you will write? You will write just the name of the list that you are using as a stack dot pop function. So what it will do? It will remove the last value from the stack and it will return it to you. I think you know the working of pop function. It removes the last value and it returns it. Okay. So these are the Python implementation of stack. Simple, one line implementation. One line for peek function, one line for push and one line for pop. So it is very easy to implement stack in Python. You will see the complete program of this stack implementation in Python in the practical session that we'll be having in the next video lesson. We will discuss the practical details of this stack implementation. Okay. Now, just covering the theoretical part in this video lesson, we will be moving on to the stack applications. Where will you use this stack? Okay, the first application of stack is reversing a string or reversing a line. So if you have given a question that you are given with a string and you want to reverse it, so using the property of a stack, what is the property? LIFO, last in first out. So if you use the property of a stack and you put that string in a stack and implement it, then when you pop the elements, it will be popped in the LIFO manner, last in first out. So that will help you in reversing a string. Next application is converting infix expression to postfix expression. There are three types of expressions in arithmetic. Number one is infix, where the operator is placed between the operands. Number two is prefix, where the operator is placed before the operands. And the next one is called postfix, where the operator is placed after the operands. Suppose you have two operands A and B. So if you write A plus B, it is an infix notation. If you write plus AB, this is prefix notation. And if you write AB plus, then it will be called postfix notation. All these three notations are called combined together are called Polish notations. Okay. So if you want to convert infix expression to postfix expression, then you will use stack. Similarly, a third application of this stack is evaluation of a postfix expression. If you are given a postfix expression and you have to evaluate it, what will be the answer of that arithmetic expression? You can use stack in it. Okay. So the second and the third application we will be discussing with the algorithm of it and an example of it, because it is very important and very interesting. Okay. So are you ready? Okay, let's move forward. Now we will be discussing the algorithm, the way to convert infix notation to postfix notation. Suppose x is the name of that arithmetic expression that is written in infix notation, and it is to be converted into the postfix expression, and we are calling that expression with the name y. Okay, so what are the steps? Let us see. The first step is push an opening bracket onto the stack. Okay, and add a closing bracket at the end of the arithmetic expression x. Okay, so what are the three things you have? You are having x, that is the arithmetic expression written in infix notation. You are having a postfix expression called y, and you are having a stack. Okay, these are the three things. So what you will do it, in the first step you will push an opening bracket onto the stack, and you will add a closing bracket to the end of the infix expression. Okay, now in the second step you will start scanning that infix expression from left to right, and you will repeat the steps 3 to 6 for each element of x until the stack is empty. So this is the bounding condition, that the stack must be empty. Okay, so you will scan each element of x, that is the arithmetic expression written in infix notation, from left to right, and you will repeat the steps 3 to 6. Okay, so what is the third step? So now you are scanning that expression from left to right portion. So if you encounter an operand, okay, I think you know the difference between operand and operator. The values on which the operation is performed are called operands, and the signature, the sign that you use for that operation is called operator. Okay, so while scanning the expression x from left to right, if you encounter an operand, what you will do is you will just add that operand to y without putting it into the stack. Okay, so the rule is each and every operand will be put in the result expression y. Very easy. Now step number 4. If you encounter or if you find a left parenthesis, that is opening parenthesis, then you will put that opening parenthesis onto the stack. Step number 5, if you find an operator, okay, what you will do is you will pop from the stack and add to the resultant expression each operator that has the same precedence or higher precedence than the operator that you have encountered. This is very tricky. This is the main thing that you have to understand. Suppose you encounter an operator, multiplication operator, okay, and in the stack there is an operator that is division operator, and you know the precedence of multiplication and division is same. Okay, so you will pop that division operator from the stack and you will add it to y, and this process will continue until you find an operator having less precedence than the operator that you have encountered. So if you have encountered a multiplication operator and in the stack you are having division operator, then you will put that division operator in stack. And again, if you encounter an operator having same precedence or higher precedence than that operator, again you will pop it from the stack and put it into the resultant expression y. Same process will continue, and if the process is complete, you will add or you will push the operator that you are scanning, that you have encountered, and you will push that operator onto the stack. That means if you have encountered a multiplication operator, then after removing all those operators from the stack that are having higher or same precedence through that multiplication operator, you will push that multiplication operator onto the stack. This thing will be very clear to you in the example that we will be discussing very soon, and in the separate video lesson we will be discussing the examples of this infix to postfix conversion also. Okay, the step 6, if you find a right parenthesis or a closing bracket, what you will do is you will pop each element from the stack and add those elements to the result y until you encounter a opening parenthesis or left parenthesis. And as soon as you encounter a left parenthesis, the left parenthesis and the right parenthesis will be nullified. So they will not be going to the resultant expression, because the postfix expression does not support these parentheses. These parentheses are just made for infix expression to increase the precedence of operator. But in postfix expression, there is no place of these opening and closing brackets. Okay, so you should take care that there should be no brackets opening or closing in the resultant expression that is called y. So this is the algorithm to convert infix to postfix. Okay, so let us see an example and the thing will be very clear to you. You see here, this is the infix expression given to you with lots of brackets and lots of operators. This operator is for exponential operator power, e to the power f. Okay, so what you have done is, in the first step you have put opening bracket in stack and you have added a closing bracket at the end of this infix expression. Now starting from left to right, first you encounter a, you put it in the result expression. Okay, then you have plus will be pushed onto the stack. Then after plus you encounter opening bracket, this will move to the stack. Then you encounter b, you know operands always move to the final expression. Now you have the expression ab. Then you have star, and you push this star into this stack. Why? Because there are no operators to compare it. Okay, it is the single one. You will not go beyond this bracket, so it is working like a wall. You will not move beyond this bracket. You will just focus on the operators before this opening bracket. Okay, so this, after this opening bracket there is plus, but it will not affect the working of this multiplication operator. Okay, now you encounter C, it is ABC. Very good. Now comes the very important thing. This is minus. You have scanned the symbol minus, and when you see the position of the stack, you find that the stack is already having this multiplication operator, and this multiplication operator is having more precedence than the minus operator. So this multiplication operator will move to the postfix expression, and this minus will move to the stack. Why? Because this star operation, that is multiplication operation, is having more precedence than the difference operator. So this will be moved to the final expression, and this minus will move to the stack. And again I am saying that you will not move beyond this bracket, because bracket means wall. You cannot move beyond that wall. Now again you encounter another opening bracket, you put it in the stack. This is the rule for opening bracket. Then you encounter D, this is operand, it will be put into the postfix expression. Then you encounter divide sign, you put it on the stack because there is no other operator. Then you encounter E, E is in the postfix expression. Now you encounter power operator. You know, the precedence of power operator is the highest in as per Bodmer's rule. So this operator is here in the scanned portion. Now you see the position of stack, there is division operator. So the precedence of division operator is less than the power operator. So you will not move it into the stack. It will remain, you will not move it into the postfix expression. It will remain in the stack, and this power operator will also remain in the stack. So you must know, you must see that the operator on the rightmost side must have the highest precedence. No other operator on the left side of this should be having greater or equal precedence. This is the rule. Now you encounter F, you put it in Y, that is the final expression. Now you get a closing bracket. So what is the rule for closing bracket? Pop all the elements from the stack and put them in the final expression until you encounter opening bracket. So first you encounter power operator, because stack is last in first out. So it was the last element, so it will be popped out first. So it will move to the final expression and followed by the division operator. So both these will be popped, and these two, this closing bracket and this opening bracket, will be nullified. They will not go to the postfix expression. Okay. Now again you encounter multiplication, and you see the condition of stack, there is minus operator. So no worry, minus is having less precedence, so both will remain in the stack. Then you encounter G, G will move to the postfix expression. Then again you encounter closing bracket, then this star, the first star will move to the postfix expression, then followed by minus sign will move to the postfix expression. Then you encounter star, again multiplication operator, no problem, put it into the stack. Then you encounter H, H goes to the final postfix expression, and after H in the beginning you have put an extra closing bracket here. Then you encounter that final one, and first star will move to the postfix expression followed by plus, and these two will be nullified. Okay, so your stack is empty. So this is the final condition. So if your stack is empty and there is no element to be scanned, that means you have done the conversion right. And if there are some elements in the stack but you have scanned all the symbols of the infix expression, that means some problem is there in your implementation of that algorithm. Okay, so you must check it that you have done it correctly or not. Okay, so at the end you find this result of the conversion from infix to postfix. Clear? Try to see this example again and again and focus on this portion. It is very important. Okay, and it will be clear to you. And we will be discussing a lot of these examples in a live session. In that live session, we will be having a detailed discussion on various examples related to this infix to postfix conversion. Okay, let's move forward to evaluation of postfix. Okay, the question may arise that why we use postfix, because in postfix there is no worry about the precedence of operator, because in infix you have to put brackets and you must take care of the BODMAS rule while evaluating the expression. But in postfix there is no such precedence problem. The operator that you find first will be evaluated first. Okay, that's why we prefer postfix expression. Now the third application of stack is evaluation of the postfix expression. Okay, here again we will use stack. How? We will create a stack to store operands. We will scan the given expression from left to right, and what we will do is, if we find the element as a number, we will push it into the stack, because in the postfix expression you will only having two things, either it will be a number or it will be an operator. So if it is a number, you will put it into the stack, and if the element is an operator, you will pop the required number of operands for the operator from the stack. Okay, depending upon its arity. If it is a binary operator, you will pop two values. If it is a unary operator, you will pop only one operand from the stack. And what you will do, you will evaluate that thing and you will push the result back onto the stack. And when the expression is ended, the number that is left in the stack will be the final answer. Okay, let us understand this thing with an example. So if we have a postfix expression 456 star plus, it is not 456, okay, it is 456 multiplication sign and addition sign. This is a postfix expression and we have to evaluate it. What we will do is, we will scan it from left to right. First we find 4, we will push it onto the stack. Again we have find 5, we push it onto the stack. We find 6, again push. So what is the position of stack? 4, 5, 6. 6 is at the top and below it is 5 and below it there is 4. Now you encounter star. This star, this is multiplication sign, is a binary operator. That means it requires two operands. So you will pop two operands. First you will pop 6, then you will pop 5. Okay, and then you will multiply it, that is 30, and you will pop, you will push this result back onto the stack. So these 5 and 6 have been removed from the stack and a new entry, that is 30, has been pushed onto the stack. So the position of stack becomes 4, 30. Okay, next you encounter plus. Then again you pop two elements because it is a binary operator. So you pop 4 and 30, you place the plus operation in between and you get the 34 as result, and this 34 is pushed again onto the stack, and now the expression is over. There is no more element to be scanned, so this 34 is the result. So that is how you evaluate a postfix expression. It is very easy and it is very interesting, and you can calculate it without using stack also, but in examination you must use stack. So if you are able to understand this example, it is okay, but if you are not able to understand this example, don't worry, we will be discussing a lot more examples related to this evaluation of postfix expression in the live session. Okay, so try to understand this example. It is very easy, and if you are not able to do it, just see the live session in which we have discussed these examples and lot more of them. Okay, let's move forward in the theoretical section. Now we are having the next data structure as Q. Q is a linear structure implemented in FIFO method, first in first out. FIFO means the element inserted first would be the first one to be deleted. Okay, suppose what is the example? A queue that is made for getting the tickets. Suppose you are there in a queue for getting a cinema ticket. So the person that has arrived in that queue first will be the first one to be served, and he will leave before the remaining one. Okay, so here in queue the implementation method is first in first out. The element that has arrived first will move out first. In queue there are two ends. The insertion operation will be allowed at the end, which we call rear, that is back side at the end. Okay, and deletion will be allowed at the end, that is called front. You know, if there is a queue for getting the cinema tickets, if a new person arrives to buy a ticket, he will be placed at the rear end, and when the person has bought the ticket and he will move out from the front. So there are two ends, front and rear. Insertion is allowed at rear, deletion is allowed at the end called front. Okay, so the process of element insertion is called insert or enqueue, whereas the removal of element, this process is called delete or dequeue. Okay, here the three terms that were there in stack, these are peak, overflow and underflow. So what is peak in respect to queue? It refers to inspecting the value at the front of the queue without removing it. Okay, and the condition for overflow and underflow is like stack. If you are trying to add some element and there is no space, then it is overflow, and if you are trying to delete an element from a queue that is having no elements, then that situation is called underflow. Okay, in Python we will implement queue with the help of list. Okay, because Python offers a convenient set of methods to operate lists as queue. For peak operation, we will use the name of the list, and in the square brackets we will mention the index number, that is the front. Okay, because the peak operation is checking the value present at the front. So here queue is a list and front is an integer that is storing the position of the first element in the queue. And if you are inserting an element, that is enqueue, how you will write? You will write the name of the list that is being implemented as queue dot append, and you will provide the item, and this item will be added at the end of the queue, that is called rear. And if you want to delete an element from the queue, here you must see the difference and you must notice it. The difference from in the pop operation from the stack, here you write the name of the list dot pop, and in that bracket you provide the value 0, because in stack implementation, if you write the function pop, it removes the last element, but in queue you have to remove the first element, that is the index number 0. That's why you have to provide this index 0 compulsorily. Okay, you must note this, that this 0 must be there while you are writing the dequeue operation in queues. Okay, so it will remove the first value from the queue and it will return it back. Clear? Okay. Now we see some variations in queue. The first variation is called circular queue. So it is a linear data structure in which the operations are performed based on FIFO, you know it, and the last position is connected back to the first position to make it like a circle. In a normal queue, we can insert element until queue becomes full, but once the queue becomes full, we cannot insert the next element even if there is a space in front of the queue. Okay, so generally जो implementation of queue is like linear structure. Okay, but the problem is sometimes when you are working with a static queue and you insert elements at the end and in between you delete some elements from the front, there is a space in the front, but as you have reached the end of the queue, you cannot add any extra element in the queue. But if you make it like a circular one, okay, so then in that position you can use those places that are available in the front for the queue. Okay, so this is called circular queue implementation. Another type of queue is double-ended queue, that is called DQ. Here this DQ is a refined version of queue in which elements can be added or removed from either end, but not from the middle. So you can insert from both rear and front, and you can also delete the elements from front and rear. Okay, so then it is called DQ, double-ended queue. There are two types of DQ. Number one is input restricted DQ, where the input is restricted from only one end and deletion can be done from any end. And another is output restricted queue, where deletion is restricted and insertion is allowed from both the ends. Okay, so these are the two variants of queue. One is circular queue and another is double-ended queue. Now at the end of this lesson, let us see the applications of queue. You have seen the applications of queue in your daily life. Okay, so if you are having a single resource and there are many persons demanding for it, like there is only one printer and many computers are connected to it, so that printer will maintain a queue and the command that is given first will be operated first, that is FIFO. Similarly, in CPU task scheduling, the task that has arrived before the CPU first will be executed first. In real life scenarios, call center phone systems use queue to hold people calling them in an order until a service representative is free. You must have seen whenever you call a call center, you are given a waiting number. That your waiting number in the queue is 6. That means there are 5 more persons before you. First those 5 will be attended, then your turn will come. Okay, so in call centers the queue implementation is used. Handling of interrupts in real life system, the interrupts are handled in the same order as they arrive. First come, first serve. You must have heard this term, first come first serve basis. Many admissions in reputed or any institution are done on the first come first serve basis, or some a new course whenever it is introduced in a college. Okay, the admissions are done in first come first serve basis. So who will come, the first one will be given the opportunity first. The airport authorities use queue in situations of sharing a single runway of airport for landing and takeoff of flights. So there are various implementations of queues that you have seen in your daily life. So with this we come to the end of this chapter theoretically, but in the next video lesson we will be discussing the practical aspects of stack and queue that you have to master the art, and those practical questions will be asked in your board examinations as well as in your practical exam also. So don't miss that video lesson, and in a separate video lesson we will be discussing the examples of stack implementation, that is conversion of infix to postfix, and evaluation of postfix. That will be a live session and you will be notified about that live lesson, and don't forget to join that live lesson. Okay, so we will be meeting in the next video lesson. Till then, be safe and keep studying.